field for many a time, and also I think she was very active in the field of element development, also constitutive modeling, and now really she's moved to the area of multi-scale modeling, which is obviously the next challenge.
Certainly not completely.
Yeah. In time? Okay. Okay, Stephanie, please carry on.
Thank you very much for the nice introduction, Roger. So the topic is computational inelasticity at different scales. We would like to move today beyond finite element technology. Would like to go to phase field modeling and model reduction. And I would like to first acknowledge my co-authors. Julian Kochmann is doing his PhD, and he has done the work on the phase field method. Actually, it's not Dennis Kochmann, so it's the younger brother. And we found already out that it's not so often that two people of the same family are in one plenary session. Then we have Annika Rademacher. She has completed her PhD now on model order reduction, and she has recently extended her work to the multi-scale modeling. So I first would like to introduce the notion of process signatures. This makes it necessary to carry out a two-scale simulation, and in this context I will also use the phase field method. The new point for us is here that we discretize it by means of fast Fourier transforms, and we'll combine that then also with finite element technology at the macro scale. And actually, in order to further reduce the computational effort, we would like then to combine it with model order reduction, here the proper orthogonal decomposition. I will then introduce that, give two variants of that, and also come to a two-scale simulation. So to begin with, I would like to say, in the manufacturing context, there's a general aim. We want to find a suitable process for the desired modification of material and state variables. Actually, we do research on this topic in the context of a special collaborative research center in Germany, funded by the German Science Foundation. So there are a lot of researchers from manufacturing technology, but also we from the side of mechanics. So in the standard way, you have some process and you certainly have experience with it, so you know quite well what comes out then here in terms of hardness and eigenstresses. But actually what we need is the complete connection in form of a matrix. Therefore I call it here now process signature matrix. We want to have the connection between some manufacturing process called PX, for example, with the desired material modification called MMX. And then certainly this material modification is strongly connected to the evolving microstructure. We need to evaluate here grain growth, recrystallization, phase transformations, dislocation dynamics, all that. And this brings us automatically to this two-scale simulation. So we have then some specimen at the macro scale. For that, we use the finite element method, and actually we like to use our own finite element technology, which has only one Gauss point. So if we carry out a multi-scale simulation, it's certainly more efficient, at least already in that regard. And then here we would like to carry out the phase field method, which we will combine with fast Fourier transforms. Julian has already studied several examples. You see now here martensitic phase transformations, here the plastic strain, here the spring in of martensite variance, here on the right side, difficult to recognize the grain growth and coarsening. Certainly, this all is highly complicated to bring this into connection with a process. This is a difficult point here. Finally, we have the aim to really compute a process and being able to compute all that. This is the challenge. So I come here to the equations. Tom Hughes has already said a lot about the phase field method, but this is again a new, maybe application field of it. we have here the Ginzburg-Landau equation, which one can see as an evolution equation for the phase fields. We have here 3 phase fields now, the 2 martensite variants and the austenite. And you see that it depends on the free energy density psi. Certainly this has to be set up. And in order to condense the formulation, we have transferred these 3 phase fields into 1 phase field variable, which we call now here var phi or simply phi. So we have these 2 latter parts which concern the energy storage in the interface between the phases. So we have here the homogeneous part called here separation energy density, which we take out of the literature from Schmidt, Müller and others. You see here now the 3 local minima of it. -1 means the second martensite variant, phi equal to 0 is austenite, and phi equal to 1 is the first martensite variant. And then we have here as standard the gradient energy term. So, and then we need to set up, as usual, the elastic strain energy. Here we restrict ourselves to small deformations. You see now here first that we take into account some residual strain, which is only there if phi is unequal to 0. You see this here in this matrix. We have here also 2 material parameters, epsilon n and epsilon s. And then the elasticity tensor is set up according to the mixture rule of Khatchatourian 83. And here you see also this formulation, which we take out of the literature. So we come now up to solve the balance of linear momentum at the micro level. And certainly, in addition, we have to solve the Ginzburg-Landau equation. It is important now that for that we use fast Fourier transforms, which is maybe not so common. So the advantages are here: higher numerical resolution, better convergence behavior, reduced computational effort. All that is kind of known. But what is new maybe to bring it then into the context of the 2-scale simulation. Certainly several people have already worked on it, and we have mainly used the work of Michel and others. We use here a semi-implicit time integration scheme in the Fourier space. So you see this here. This here is implicit. Here this is explicitly treated, this 2. And so we come to this expression where we have here in the denominator then the transform to the Fourier space where k is the wave vector. Certainly these are long pages of derivation which I do not show here now. I come now immediately to the examples for this first part. So we have here now a single element with an austenite matrix and a martensitic inclusion in order to initiate the phase transformation at all, otherwise nothing would happen. And we have now different loadings, fast loading, moderate loading and slow loading. And you see that hardly anything happens for the fast loading. This is simply too fast for the phase transformation to take really place. But if you have the middle loading and the slow loading, then a lot of things happen. For the slow loading, you see here clearly elliptic shape now of this inclusion. Also the austenite matrix has almost vanished, and the second martensite variant has come into play. You see here in the stress-strain diagram that for the 2 upper numbers here, hardly any change is visible, but for the slow loading, you see here clear nonlinearity in the stress-strain path. So this is also seen then in the stress patterns, here the y-y direction, and here the shear stress. Also there, a lot of happens then for the slow loading. So this was only a single element case. Then we studied polygrain structure. You see now also here the material parameters, here the elasticity constants. Then these 3 parameters here concern the interface part of the strain energy density. Then we have here the mobility, and then also the 2 parameters for the residual strain. And these numbers here refer to the number of sample points for the Fourier space. So you see here the specimen, quite classical still. So the lines indicate that the displacements perpendicular to them are 0. And we see now the phase transformation happening at the microscale. So we start again here with pure austenite. So this is then blue in blue color. Please don't be confused. I mean, we have here the volume fraction for the austenite, which goes from 0 to 1. So this is now pure red, which means also only austenite at the macro level. Then the martensite variants come into play. This starts here, and obviously then the austenite volume fraction goes down. And then even more martensite comes into play, and obviously here it goes further down. So this looks reasonable, and one can compute it. So here are the stress distributions for different times. So different stresses also. So we have first here the horizontal stress component. Tx is for us here the stress tensor. Then the vertical component, and here also the shear component. So this is possible. Certainly, still, this takes a lot of time. Therefore, I will come immediately to the second part of my talk. But this is in any case already possible, feasible, and gives quite nice results. So for this algorithm, actually, it is not possible to carry out the linearization procedure analytically. Therefore, Julian has here developed a numerical scheme, and you see that this converges also quite nicely. So I would like to finish this part. I would like to emphasize again, the new point is here the combination of a phase field method discretized by fast Fourier transforms with the finite element technology at the macro scale. This is, to our knowledge, a new point and shows a quite nice computational efficiency. Certainly we have to prove this quantitatively. This is still ongoing work to see the comparison to a classical FE approach. However, it's obvious we still have here a lot of computational effort, clear, and we would like to further reduce it. And we had the idea to compute this microscale by means of model order reduction. Certainly we are not the first ones who try that, but I think our way is then also new. So I would like to come to the model order reduction topic now. So we have now here a completely general nonlinear vector equation. This is now already here the global finite element level. This can be any material behavior. U is the global vector of nodal displacements. Everything is here implemented into FEAP, finite element analysis program, developed mainly at the UC Berkeley by Bob Taylor. So the idea of model order reduction is to come down from the original number of degrees of freedom n to a much smaller number m. And using projection-based model order reduction, this is done in the way that we multiply here in this way with a projection matrix phi. Certainly this has to be set up now, and for that we want to use the proper orthogonal decomposition. Certainly this method has also been known, but I would like to emphasize that its application in the context of nonlinear solid mechanics is also not so frequent. In this context, we have done some work during the recent years. So you see now here the phi. So how is it constructed? We compute so-called snapshots. So we investigate a specimen offline. So this is work in preparation before we carry out the actual online simulation. We store these snapshots, arbitrary deformation states away into the snapshot matrix D. Then we formulate the eigenvalue problem of the corresponding correlation matrix. Then you can look at the eigenvalues. Some eigenvalues are almost zero, so the corresponding eigenvectors are thrown away. But we take the significant eigenvectors, which belong to significant eigenvalues, and put them now into this matrix. So, and now this has to be used, certainly. We started here with nonlinear elasticity, so we started first with problems of biomechanics. So you see here the finite element model extracted from that. We have here nonlinear elasticity. And you see now already here the CPU time effort over the reduction order. So 99.95% means that we keep only 5 degrees of freedom out of 1,000. So this is already a quite nice reduction. And the CPU time effort has come down quite a lot, but certainly this percentage is not so meaningful, because you could certainly discretize your finite element model also by 2 million of finite elements. Then we would end here up with much smaller numbers. So this is only for orientation here. It's important to say that the accuracy is extremely low also. This is important, the error here of this simulation, which is only 10 to the minus 6. And as engineers, we would like to look also at pictures. We did that too. We looked at the stress patterns, and actually you cannot really make out any difference between these two computations. So this is quite nice, and this works quite well. So, but however, in the mathematical literature, some method circles around, which is quite interesting. It is called Discrete Empirical Interpolation method. And the idea is to split the residual force vector into a linear part and into a nonlinear part. The linear part can be also treated kind of offline. So it's anyway constant. It does not cause any additional numerical effort. This is seen here below in this equation. And this part now is certainly quite elaborate, because there the constitutive behavior, which is different in every Gauss point, comes into play. And here one makes another reduction. One chooses only a selection of evaluation points where the constitutive behavior is computed. This certainly gives us another reduction in CPU time effort. So you can imagine that as another model reduction, which is here carried out. And we have had success with that. So we could come down from 3% to 0.4%. These percentages here refer always to the CPU time effort of the full finite element system for this structure. You see here different case. These are now the resulting number of evaluation points, 5, 10, and 20. If we look at the error, then actually for k equal to 5, the error is actually not so small. But already for k equal to 10 and k equal to 20, this is very nice. And if you look again at the stress patterns, then even for k equal to 5, you do not see any difference with the naked eye. Okay, this sounds very nice, but the unfortunate thing about it is that it really works very nice for elasticity, for nonlinear elasticity in our case. However, for plasticity, it is not so good yet. And certainly we approached mathematicians to look at this problem, especially Dani Sørensen, but he has not replied to us yet. Certainly for the mathematicians, this is really a very terrible problem, the plasticity. We fully understand that, but for us it's certainly quite not so nice. We would like to have this solution. So in the meantime, we had to go around it. Certainly we have a lot of problems concerning plasticity. This is here, for example, an incremental forming problem. And here we would like to apply it too. We have here large elastic and large plastic deformations. And if we apply standard POD, as I just presented it, then actually we get here quite high errors. So we came to the idea to apply here a method of substructuring and to apply model order reduction only in the elastic regions of the structure. Certainly plasticity is changing all the time, so this has to be done then adaptively. Actually, this works quite well. This is now the name of this method, adaptive selective POD. So at the beginning, there's no plastification. Therefore, model reduction is applied everywhere. Then plasticity comes into play. You see this here. And then, obviously, the area where model reduction is applied becomes smaller and smaller. So if we then compare that, you have here the so-called unreduced simulation, where we did not carry out model reduction at all. Here you have the result of the POD, of the standard, where you apply model reduction everywhere. And then here the result of our adaptive selective POD. And obviously, now with the naked eye, these two agree quite well with each other. This here is simply a little wrong. And the same here for the plastic strain. And this carries also over to more complicated cases. There you see this even more clearly. I hope that I can get this here now. This is here the free-forming situation, quite complex problem already. And if you now compare it, so for the adaptive SPOD, quite good agreement, however here wrong, or let me say, kind of not so good results. Okay, we have been at the status, and then we came now to the idea of using model reduction in the context of two-scale simulation. So this is now also the macrostructure, which is an airplane. Certainly it can be anything. We have here the Gauss point. Then, as usual, we get here the macroscopic strain states. We applied this also for large deformations, therefore here also the F-bar, deformation gradient. This is here an RVE for a fiber-reinforced material, and we would like then to make another step, do model order reduction for this RVE. Therefore, we call this now POD RVE, and we would like to give back the averaged stresses and tangents as usual. So on the boundary of this RVE, the displacements UB are prescribed via then these macroscopic strain measures as usual. We assume here periodic boundary conditions, and we need to compute in the inner domain of this RVE then obviously the displacements, which are called here UF. So how is the situation? We have here equilibrium, certainly for the RVE to fulfill, as I said before, for the context of the phase field method. So we have split this now into boundary and inner domain two parts. Let us look first at the inner domain. And here now the model order reduction is applied. So we simply say that UF is now equal to phi URET. This is the same reduction which we have before applied to the macroscopic structure. And then everything is more or less done the same. You then compute at the micro level this problem here. Certainly, due to the fact that this K-ret is a very small matrix, maybe 5 by 5 or so, this is extremely easy to solve this equation, or let me say fast, whereas before, certainly in the KFF, a big number of degrees of freedom were involved. Certainly, I did not say here much about it. We set up these matrices at the element level, and there are tricks to make it more efficient and so on. All these tricks can be certainly used here too. So this is quite now much, much faster. Let's continue. We have now here this solution achieved. We have computed UF. UB was also prescribed. And so we have certainly here 0 in the way that we have now a load vector which comes from the prescribed boundary displacements and from the newly computed field displacements. The next issue is now to determine the averaged stress and tangent. For that, we exploit a formula which one can find, for example, in Kuznetsova 2002. So you have here the integral over the boundary, over the stress vector, and here dyadic product with the position vector x. So we can express this in this way, where the load vector LB enters this formula. You can now carry out the linearization as we did it here, and you get again here the use of our model order reduction in a consistent way, and you can then also compute finally the tangent C, which is then here kind of tangent matrix, the one which is needed in order to get here very good conversions at the macro level then finally, including then the behavior at the micro level. So we come now to several examples. This is very simple, the simplest one, a linear elastic RVE, but certainly it should work for it, obviously. So the fibers are orthotropic, the matrix is isotropic, we have periodic boundary conditions, and we use now logically 6 precomputations for the different strain states. So this is done offline now. These 6 precomputations which let us now establish the projection matrix phi, which I discussed before. And if we do this in this way, then we get actually an exact result here, because it's linear elasticity. And this is very simple. So this is the result of the unreduced simulation. This is the result of the reduced simulation. And the error is simply 0. But the speed up is 60, which is already a good, let me say, success. We have compared that with another multiscale method, which is called high fidelity generalized method of cells. This is used at NASA Glenn Research Center and has been developed there also. And this is also a very good, strong method, but you see here certain deviations, certainly only quantitatively. Qualitatively, these methods agree very well. So we have then made this a little more complicated, went over to elastoplastic RVE. So here the matrix is now elastoplastic. Again, periodic boundary conditions. First, we used, again, only 6 pre-computations. So the reduced number of degrees of freedom was 6. Certainly you can also use more, as I will explain immediately. And for the 6, you get here actually a slight mistake. It's not much, but you see slight differences. Now, if you compare with the naked eye, it's not the same. Also for the HFGMC differences, okay, but it's qualitatively in a good order. So we used, after that, 25 degrees of freedom for the reduced model. And here again now you see the change, improvement. So there is convergence, at least in our engineering sense, to the unreduced system. Quite good agreement now. And this is also visible in the error. If you put this down, you see for the HFGMC here a quite big error for the stress 1, 2. For our method, this error is even higher for the 2, 3 shear stress. But actually, you can bring it down by simply using more degrees of freedom, which is clear. No? This is well known for the POD method, but it's nice that one can see this here also. And it's really brand new work, I have to say. Therefore, we are not so far yet concerning the real structures. So at the moment, this is here only one element practically with a kind of complicated loading. And you see here already in a good agreement for the simple example between FE2 and FE-POD. Actually, what is always very nice here is that we have a speed up of 170. I think I forgot to say that for the plastic example, which is very nice, we had a speed up of 300. No? So you see noticeable reductions in CPU time, and certainly one has to make really further research on that. So with that, I would like to come to the end. So for us, it was really a new topic here, and we see now that the combination of multi-scale simulation with POD is possible and promising. Certainly, we would like to combine that with the phase field method. This would be really interesting. We are not the first ones who have tried this out, but I think these methods are different. Suke has applied the model order reduction on the internal variables. He has not worked with the displacement, so this is slightly different. He has recently presented that on the ESMC in Madrid. Extreme speed up also in 700 or 1,000 or something like that. This is really extremely interesting. And his idea maybe can apply it also here. We would like to cooperate at this point also maybe with Pedro Ponte Castaneda. Julian Kochmann is visiting him right now. Would be nice to not need this going back to the full matrices all the time. At the moment, we always evaluate also the full, let me say, representation, finite element representation in each iteration. Maybe this can be avoided, and then we would be even faster. In general, for model order reduction, there are many interesting open fields of application. System identification, stochastic analysis, this is still starting. And what is clearly open and probably will remain open for the next decades is the choice of the snapshots, and maybe to include more complex material behavior, maybe also from the mathematical side. At the moment, we certainly are able to do that, but we are kind of lost in what concerns proofs and further mathematical statements. Thank you for your attention, and here are pictures of the main two contributors, Annika Rademacher und Julian Kochmann.
Thank you, Stefanie. It's a very nice lecture.